Good day everyone. For this presentation, I'll be explaining a Python code that performs simultaneous time and amplitude transformation on a discrete time sinusoidal signal. In this activity, we explore how a signal behaves when we modify both its time characteristics like shifting, reversal, or scaling, and its amplitude characteristics like amplification, attenuation, or inversion. We'll be using NumPy for mathematical operations and aMpLiTUDe for visualization. Step 1. Importing necessary libraries. Here, NumPy is used to handle arrays and mathematical computations such as sign, functions, and range values. aMpLiTUDe.pyplot is imported as PLT, which helps us plot the discrete time signals using stems plot. These are perfect for visualizing individual signal samples. Step 2. Generate the original signal. Let's break this down. N creates discrete time indices from -10 to +10, giving us 21 sample points centered at 0. X defined our original signal as sinusoidal function sin 0.3 pi n, a discrete sine wave that oscillates smoothly between -1 and +1. This signal will serve as the base reference for all the transformation we'll apply later. Plotting the original signal. Here, the program creates new figure windows using plt.figure, plots a stem graph showing vertical lines for each discrete value of the sine wave, label the axes, enable a grid for clarity. The result shows a centered sinusoidal pattern symmetric around n is equal to 0. Step 3. Apply simultaneous time plus amplitude transformation. This is the core of the code. We apply the three different combinations of transformation, one for each plot. A. Amplified and time-shifted signal. The amplitude is multiplied by 2, which doubles the height of the signal. The term n-3 introduces a time shift of +3 sample, which means the signal is delayed or moved to the right. The results, the wave looks taller and shifted to the right compared to the original. B. Attenuated and time-reversed signal. Multiplying by 0.5 reduces the amplitude, creating an attenuated signal. The term -n reverses the time axis, effectively flipping the waveform horizontally. What was on the right now appears on the left. The result, signal appears smaller in amplitude and mirrored around the vertical axis. C. Inverted and time-scaled signal. Multiplying by -1 inverts the signal, flipping it vertically. The term 2 multiplied by n applies time scaling or compression, which makes the signal faster or more compressed along the time axis. Result: signal becomes inverted and tighter, with more oscillations visible over the same time range. Step 4. Plot all combined results. The next sections display all three transformations in one figure for comparison. This sets up a larger plotting window to fit all three subplots. Plot 1. Amplified plus time shifted. In this first subplot, you'll notice the peaks are taller and the signal is shifted right. It visually demonstrates the effect of amplification and delay. Plot 2. Attenuated plus time reversed. The second subplot shows a mirrored waveform that is similar in height, clearly showing both reversal and attenuation together. Plot 3. Inverted plus time scaled. In the third subplot, the wave is upside down due to inversion. It also appears more compressed because of the scaling factor 2, meaning more cycles fit into the same time frame. After running the program, we observed the following outcomes. Amplified plus shifted signal, the sine wave appears taller and moved to the right. Attenuated plus reverse signal, the signal becomes smaller and flipped horizontally. Inverted plus scaled signal, the waveform is upside down and compressed in time. So together, these demonstrate how multiple transformation can affect a discrete time signal's shape, timing, and amplitude simultaneously. So in summary, this code combines the core operation we have learned so far. Amplitude transformation, which amplify, attenuate, invert, and time transformation like shifting, reversing, and scaling.